participant today to understand more about this technology. For myself, yeah, I like to know more because I want to apply for geothermal exploration. So to others that just joined us, now we already have around 61 participants, Mr. Rek.
Right.
So 3D geologic mapping with electromagnetic is, I think, interesting topic. So I hope that we can have maybe almost 100 participants online, and then everyone have free time to do anything else. So without any ado, I think you can start with your some introduction about your background, and then you can follow with the presentation. Okay, the floor is yours.
Okay. Yeah.
Thank
Thank
you.
you, Doc Hariri. Yeah. So, yeah, my name is Rex Camit, and I'm a member of Geological Society of the Philippines. Same with Dr. Ramos, and I immigrated to Canada 2002. So I've been with PNOC EDC, which you might have known was the leading geothermal company back then. Probably until now. So I worked with them for 12 years. And then when I went to Canada, I'm into like mixed mining, mineral exploration, and then geothermal, since that's my passion. Yeah. So, okay. We start now with the presentation. Okay, 3D GEM. So what's 3D GEM? Three-dimensional geologic mapping with electromagnetics. And just to mention, the main man behind this technology is Dr. Emmanuel Ramos. Okay, for 3D GEM, we use ubiquitous ambient electromagnetic waves that are recorded by 3D GEM. And the capture and processing system employ all electromagnetic sensor components. Just to be familiar with the letters here, the G is for the GPS, location and time. So this is associated with the data recorder that we have in each unit. And of course, this is powered by a battery. And based on these schematics, you can see all the sensors that we're using is biaxial or triaxial electric sensors, shown by the letter E, and then the H, which is the triaxial magnetometer. So this technology is, you can say, built upon the principles of telluric principle. Yeah. So just to give you an idea about the processing, this technology creates a dense cloud of electromagnetic information. An example is you have this multiple sensor combination, like you have your site 1 and site 2, and this is very important because the instrument or the station, each station has a multiple sensor combination like EX1, EY, HX1, HY1, SZ1, and it combines with the sensors at site number 2, which is EX2, EY2, XX2. So those kind of combination. And just to give you an idea, 8 sites will create 28 additional data points. And you can see here, it depends on the geometry of the target deposit or target area. You can have a dense instrument in the center and probably a little bit of less denser on the outer side, but it's still better to have a good coverage of the area. So just to give you an idea on the layout, ideally, you have this 25 3D GEM sites, and it's capable of creating or extracting 325 3D GEM profiles. And with this, you have more than 6,000 data points due to this layout. And just to give you an idea about 3D GEM, the patent claim is that geologic features are mapped. So it's mainly qualitative, not quantitative. So you can map faults, beddings, folds, structures, and then you can see transitions between units, lithologies, and texture, or probably chemical composition. So this also plots a geological model. So no numerical manipulation is involved. So probably you've heard about those third-party modeling software. They brag and saying that, okay, we have this. You have all your geophysical section, and we can do 3D modeling. So 3D GM is not like that. So, okay, based also on 3D GM, it's based on empirical observation. And there are two modes, one for structures, which is mode B, and one for anomalies, geophysical anomalies, which is mode A. And just to give an idea, um, it's akin to a 3D seismic, wherein you have your bedding structure in sedimentary regions. It's correlating all your layers and units between sites. So there's no, it's automatic. And there's no like uh, interpolation, extrapolation to an nth degree. And you have your high resolution 3D images. So really high density data points. And of course, mode A, like resistivity, is really mimic extended from the second data, and other forms of electromagnetic anomalies that we see from the data. So just to give an idea, it's passive. It's a passive passive method done by the ubiquitous signatures of electromagnetics, and it's nodal and it's lightweight. So this technology, you only have short deployment, like 4 hours, 500 meters depth. Just that's the initial, and the signal stacking. If you have 20, so the longer you have, you expose the target area like 24 hours, the deeper you get in getting all those data, even at least 2.5 kilometers depth. So as what I mentioned in the previous slide, there is no numerical modeling involved. So just simple data interpolation and plotting, and it's automatic. And the results are self-explaining, really high definition 3D images. So as what I mentioned, we have the mode A and mode B. And just to give you an idea, mode A is for the anomalies, and then mode B for geological structures. Okay, what to expect? So in mode B, as what I mentioned, it's mostly geological structures. It's governed by electromagnetic impedance distribution in a geologic profile. And it uniformly increases with depth. So you can also see on this mode, it's disrupted by structures such as fault and other discontinuities. It's really very clear, and it follows bedding of sedimentary units. While for mode A, you can see all the electromagnetic anomalies, and it's governed by electric and magnetic features of the earth materials. And images are composed of islands of values. Example is hydrothermal alterations that show affinity to faults. So just to give you a flavor of what 3D GM offers. So you have your faults, and it's very prominent in mode B, fluid surface in mode A, your geophysical anomalies, MOFET structure I will be showing in the next slides, especially in geothermal. And then Schlieren structure, alteration clay deposits, motile texture, bedding and folds, homogeneous mass, dikes narrow intrusions, which is very evident in mode A, and discontinuities, of course. So I'll be presenting 4 case study, and this is the first one. So in this case, it's a karst geology. So it's it consists of thick young limestone beds with cavities, and this is in mode A. So if you see here, there are some like 2D profiles, an existing data of the area, and we try to see how it mimics all of those 2D profiles. So just imagine the clouded area, those blue, green, yellow ones are 3D GEM, and you can see all of those random distributed 2D profiles. So just to, okay, there. Okay. So just to, I like to pause it so at least you have an idea, what it entails. Most of the cavities are, you can see you have your red high resistivity zones, and then your low resistivity, which is the blue one. So you can see it's very clear showing all of those cavities here. And I have to make it active again. And you can see even, on section view. I mean, just imagine you have all of those 2D profiles, but what's in between? And that's where 3D GEM comes into effect, wherein it will fill in the gap and give you an idea, okay, there are more cavities than what this 2D profile are really showing. Now we go to the next slide. Okay. Yeah, it's in mode B now. We're showing the geology, and to the bottom is the resistivity, the mode A that I've shown in the previous slide. And I have to stop again. Yeah, something like that. So I have to move it here. Okay. So in this specific area, it's the same area that I've shown in the previous slide. You can see here, it does show an upthrusted terrain. As it's in Google Earth, you can see this, and it's confirmed by 3D GEM. You can see this displacement here of this green band here compared to this one on the left. So it's clear that it's an upthrusted terrain based on the discontinuity or continuity of those layers. Yeah. Okay, now we go to case 2. And there were previous work done here wherein they mapped shallow dipping waki, siltstone, and conglomerate. So this is a proposed dam. And what happened is existing data, they have a very low frequency 2D profile at the, you can say, north bank, south bank. And it will be shown on the next slide. But here in this case, it's in mode B, geology compared with field geology data and geophysical profiles. So you can see all those layers showing, you can say it's suggesting the geology for that area. And if just to give an idea about the 2D resistivity, you can see this like plain curving anomalies shown on this 2D resistivity. But with 3D GEM, it reveals a syncline. So you can see it's very clear. even if it's laid because it's in 3D, you can you have an idea on how to integrate the 2D resistivity profile with our 3D GEM, and it mimics it. And with further detail, with more details that we can see. Okay, now this is the result of that work, wherein it shows, I have to stop again to show the two 2D resistivity profile. So actually it's here, but it's there. Okay. Oh, there. Oops. Okay. Okay, have to go back again. Have to stop it exactly when. Okay, probably here. Okay, there. Okay, so you can see your very low frequency resistivity to the profile. So just imagine the river runs through in between. So this is like probably the north bank, the south bank is southwest here, and then the north bank there. So so you can see here, this is in mode B. So you can see all of those syncline structures. It's very clear. And then not only that, based on this case study, it was I remember it was like 24-hour exposure, and we even penetrated deep until 2,500 meters. And if you can see, there are some like definition of those bands. Yeah, right. Sedimentary, probably more sedimentary rocks, riffle limestone, question mark, or faulted igneous rocks. So it's open to interpretation, of course. And you just have to go all the data that is available. And as what mentioned in this slide, it penetrates until 2.5 at least. So that is just 24 hours. If you go longer than that, it might go deeper. Okay. Now, this is case 3, tunnel geology. So this was done it's for a water conveyance tunnel. So just to prepare tunnel excavation for structural and water influx hazards. So before they have some probably old maps or old mapping done, and they were saying that they have mapped an inclined fault like this from the surface exposure. And they're saying probably will encounter inclined structures. And of course, that would be, it would have an impact on the tunneling done on this area. But due to 3D GEM, they were able to yeah, this one is for geology, so it's mode B. So you can see there are some structures like that, and it's like it's indicating there might be like vertical structures, not inclined, and that would be very important for those doing the tunneling. And yeah, they would have some corrections on how to do their tunneling, and that will be helpful. And as what mentioned here, yeah, it's all various volcanics, and the color bands, it's a reflection of the electromagnetic impedance variation in those geologic materials. And an example of this is when they were doing the tunneling, they encountered an andesite with slickened sides, and it's really a vertical structure, not the previous inclined structure that they have mapped before. So that's mode B. And now this is mode A, wherein it also confirms the structure, although you have these color bands, which is also an electromagnetic impedance, suggesting that this alteration by groundwater might be due to the vertical structures that that 3D GEM interpreted in the previous slide. So that would have a big impact on the tunneling that they planned for this area. Just to give you an idea, Google Earth, it's saying that, okay, vertical faults are really evident in the area. You can see this structure here. So the red one is the new tunnel, and the yellow is the older tunnel. And the coverage of the 3D GM data is here, only here. Those are the limits. Yeah. Okay, now we go to case 4, which is the geothermal case study. And I hope I can give you a better explanation about how 3D GEM was used in this case study. So, this area has been like done like previous work like geologic maps, surface and drill holes, magnetotelluric surveys, and other geothermal data, probably hit data, something like that. So what happened is we are planning to compare all of this data with 3D GEM with use of the modes A and modes B. And just to give you an idea, we use 25 3D GEM instruments here, and they were given 24 hours exposure, and which resulted to 325 1D profiles. And just to give you an idea, the faults are these yellow lines here. Yeah. And then the colors, of course, the geothermal resource itself. And just to give you an idea of those 1D profiles, I have a video here showing vertical cuts of the 3D GM profile. And I will play it right now. Okay. Yeah, so you can see there are some textures being shown here. And as what mentioned here on the slide, you have your scleron, which is this one here. And it mostly suggests a structure, which is consistent with the structures they have mapped before. And there are some parallel structures that were not mapped. So there were additional structures. And the Moffett, actually it should, okay, I'll show it again on the next video here. Okay. We also map a Moffett structure, which suggests a thermal plume in the middle of the reservoir. And it shows almost here. So those are the features that we consistently see using 3D GEM, and that's only mode B. Okay, and now we go to mode A. Okay. Okay, so now mode A will be looking for other Schlieren textures and mottled, concentrating on altered grounds that is evident within that area. And yeah, we have compared it also with their geophysical surveys done. And this is an example of the mottled texture, and which suggestive of the altered grounds in that area, and also fluid flow. So there's another video and another vertical 1D profile showing 3D GEM. So you can see altered grounds really prevalent from surface until this level here. Okay, so just to give you an idea, you might have not caught it on the previous slide, but very subtle. You can see there are structures like this vertical fault here, and then we see that that structure could be like geothermal fluid rising from depth. And then actually this structure here, this inclined structure here, which is actually associated with the nearby lake, we see that could be associated with groundwater influx from nearby lake. And it's really an active fluid channel for that area. And this was not mapped by the owner, I mean, of that geothermal field. And they see the advantages of using 3D GEM. And of course, your altered grounds here. Yeah, same thing. This inclined structure here, we suspect it having that groundwater influx coming from the nearby lake. And of course, the detail of the vertical magnetotelluric chart, which mimics what we see in 3D GEM. And it even shows shallow groundwater influx because of this structure here. And okay, these are the limit for the 3D GM data. So it's all about accessing the area. Ideally, we should really cover certain areas wherein we have to have like a good view of the data. And yeah, based on this, the vertical fault identified in 3D GEM also affects the deformed clay cap because of that groundwater influx too. So groundwater deep into the reservoir, and it is confirmed even by data from drilling and even reservoir that there is really incursion of this groundwater from those structure. There are some temperature inversions, you can say, from their data, and 3D GEM confirms that. And the image to the right, it shows how the reservoir itself looked like, and it's consistent with the magnetotelluric resistivity interpretation. Although we're showing it in 3D, which is very good. I mean, this is your reservoir, and 3D GEM gives that configuration to you in 3D. Okay, sorry. And that's in mode A. Yeah. Okay. What are the advantage of 3D GEM? As what I mentioned before, you only have 2D images and you have like pixelated 3D, which is very common in traditional geophysical methods. And you have those gaps. And of course, 3D GEM fill in those gaps. And then, of course, common 3D geological models is what I mentioned before. There are some commercial modeling software that would say, okay, we'll have a good interpolation, extrapolation of your deposit, of your target area, and it's very hypothetical. But with 3D GEM, it's all in high resolution 3D, data plots as model, and it's automatic. And you can see a version of its geological interpretation and its geophysical. And just to emphasize, there are different applications: structural geology, tectonics, hydrogeology, oil and gas, structures, mineral exploration, of course, geothermal, which you can see it's been proven here on this on the case study number 4. And yeah, actually, we're looking into carbon capture and storage too. So there are still other applications that we can use 3D GEM. And as what I mentioned in the previous slide, it was, yeah, the next slide would show you that. Okay. It has a patent pending in 5 countries and patent application postponed in 1 country, which is Australia. So you can see Philippines, USA, Canada, Netherlands. Okay, of course, Philippines. I mean, as what I've discussed with Dr. Ramos, if we have this technology, why not share it to Southeast Asia or Asia? I mean, first, before these countries. But of course, we need to get interest from yeah, different stakeholders of our neighboring countries, of course. And just to give you an idea, 3GEM as an intellectual property protection application, as shown here: Philippines, Netherlands, UK, and this is still new, November 2024, it's still hot. And then USA, Canada, Australia. So to cap this up, 3D gives you a clearer view of the subsurface. And we've shown this on the 4th case study I've been presenting in the previous slide. So that ends my presentation. And now the question and answer portion.
Okay, Dr. Red, thank you.
Thank you.
Sorry, I have problem with the camera. So Mr. Abdul Majid will continue to moderate for Q&A session. Please welcome Abdul Majid.
Thank you, Dr. Riri.
Thank you very much, Mr. Rex Camit, for that informative and engaging presentation. That was a great presentation. Now let's move on to our Q&A session. If you have any questions for Mr. Camit, please feel free to type them in the chat box or raise your hand if you would like to ask directly. The first question was in the chat box from Mr. Lee Carwi, and I guess in the model B for the MT. He asked, what does the color's intensity signify in mode?
Where's the...
In mode B, yeah, in mode B, the color attributes. The first question. Is it clear, the question, or...
Can I cannot see the
Can I ask directly?
do I have to stop the I shouldn't stop the sharing. I cannot see the question box.
The question was, what does the color intensity signify in mode B? The color attributes.
Well, generally it's resistivity values and right now, it follows the electromagnetic resistivity values. That's the main thing. But I did ask Dr. Ramos about this, and uh, f- for now, it's still safe to say that it's mainly resistivity values. Yeah.
Thank you, Mr. I hope the answer is clear to Mr. Lee Carly.
Okay.
Okay.
I cannot
Would you like
see
to share?
the.
Would you like to share some?
Okay. Where's the. Okay. Yeah.
You like to move the
Oh, okay. Okay. What's the first question? Where? Okay, I can access now the the chat. Okay. Okay. What does the color in mode be? Okay. Yeah. 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 It's resistivity value. Yeah. But probably Dr. Ramos can expound more on this.
Yeah, good morning. Thank you. Thank you for the question. The question is about how the resistivity was, you're talking about the resistivity, how it was arrived at. Basically, what we do is that we measure with 2D resistivity on the surface. We measure the resistivity and extrapolate from there. So basically, 3D GEM right now, we're not doing any quantitative calculations. We're more doing qualitative testing and mapping, and we're limiting to that right now. And we know that there are formulas we can use to derive, for example, impedance values or resistivity values. But right now we're not doing that, mainly because it's taking a lot of time. We're more trying to use maps rather than the values. So right now we're more after. Remember that Rex mentioned this is more for geologic mapping rather than geophysical mapping. Thank you.
Thank you for the informative answer.
I think there's a
We
second
move
question.
to the second question. Thank
So
you.
what's the maximum spatial distance of the source and receiver to still have a coherent electromagnetic impedance and structural features for 3D GEM image? Yeah, I think Dr. Ramos can explain more on this.
Okay, Rex is quite shy in answering this, but yeah, we've done tests in terms of separation between sensors, and most of the time we get good response if the two sensors are about a kilometer apart. Further than that, we get values, but it seems like we need to make corrections as we move further. And right now, what we're doing is that we're getting a separation of something like 2 to 3 kilometers between the farthest. Remember that we're using the whole network of sensors, okay? And right now, we're using the farthest distance and correlate this with those that are coincident plots of the 1D sections, and we're finding them to be good correlation. But we're not even right now. We're not even sure whether the quality would still be sustained if we get longer separation. So right now we're talking about maybe 1 kilometer as the furthest distance between two sensors. Thank you.
Thank you, Dr. Ramos. The answer is very clear. We go for the next question, which should ask an example of application in mineral exploration.
Yeah, if you can see from the previous slide, I think case one and Yeah, case one. It's very useful in structural mapping, and like for example, if it's like uh, a gold structure wherein there I remember working in a gold exploration company. There are times wherein those gold veins have been displaced for probably 50, 100 meters, or depending on the displacement. And I think 3D GEM can catch this at depth. And of course, it will give you further um, um, uh, high resolution. And with that, since it's in 3D and you have your, you can say, correct XYZ, you can catch that structure at depth, with your drilling strategy for that this space structure, this space gold vein, and that would make budgeting your drilling strategies cheaper.
May,
Sorry, can I ask
may I add to that? May I add to that? Sorry, but I just need to also clarify that we are right now working on two sites in the Philippines for mineral exploration mainly. We've worked on one site, but because we were there for a short time and there were people that are protesting our presence in the mining area, so we were not able to finish that. But right now we're doing a formal survey in two mineral areas in the Philippines, and we're working on two sites in Canada right now. So we might be able to produce a sample of actual mineral exploration survey in a few months, but not right now. Thank you.
Yeah, sorry, Nathan here again. I'm just in terms. I understand this 3D GM will be able to detect structures, but the question is, if there are sulfides down there, will you be able to see that?
Yeah, in terms of resolution, if you're talking about a dike, for example, a vein that's about say half a meter wide, the spatial resolution would resolve that. I mean, like you need to have a good spatial resolution, and that's where the distribution of the instruments on the surface would work. Okay, you need to focus your instruments towards detecting that. Therefore, having an initial information of where you expect the minerals to be, the vein to be, or the orientation even, you can plan on your survey to focus on that.
Yeah,
So, yeah.
if you in the Philippines, there's a lot of porphyry copper. So how do you think that will work? If you run it on a porphyry system, will that work? Can you see you will be able to see the zone within the core and all the way to the surface, you know?
Yeah, I would expect the alteration zones to be easily mapped. Well, we in the geothermal areas, we can see the alterations very clearly, the alteration zones. What Rex was showing earlier, you can see the altered grounds on the surface. And it's interesting to see even the cellular form of the altered grounds and their relationship to the water, to the plumbing system that's creating them. So that in fact the being able to map the plumbing system even to a few meters or even thinner structures with hydrothermal fluids passing through them and creating the alteration zones. I don't think you can see any other detail from geophysical or even drilling work that can show you that.
Yeah. What's the depth again in terms of to see that in terms of resolution?
The depth we showed in the maps were 1.8 kilometers for the chart that we've shown. In terms of resolution there, I would say a meter or less for the narrow dikes or faults that were leading the fluids to the surface.
They're pretty good. Yeah. Oh, thank you. Just to know, because it's interesting to see if we can do this in mineral exploration. Thank you for the feedback. Appreciate it very much. Thank you.
Thank you.
Thank you for the clear answer. There's another question from Dean. He asked how you get the resistivity, the theory.
Yeah, basically it's Maxwell's equation. It's basically the magnetotellurics equations. We can use that for the resistivity if you're talking about that in terms of theory. But again, we would revert to saying that, look, we're not into calculations of resistivity at this time. We're more trying to discover what can we do, because right now we have other tools for doing that. We can use magnetotellurics, resistivity. We can use cabled system to do that. What we're trying to find out really is the spectrum of where we can go in terms of first geologic mapping, because we're excited about that. I mean, we're not focusing on the qualitative calculations. We're more looking at the we're not focusing on the quantitative. We're focusing more on the qualitative values for now.
I also remember it would help if you have existing data like geophysics, like what happened in the case 4, geothermal. You have your other data, geophysics, geology, structural, heat surveys. It would help. I mean, it would be complemented by 3D GEM. But based on that, you can also, like if you want to expand your area, 3D GEM would like give you an idea, or probably this is this condition here might be the same as the main resource. I mean, I'm talking about not having any data at all outside of the you can say developed area for the resource. So 3D GM at least would give you an idea what are your strategies would be when you encounter interesting structures in geology and in mode A and mode B, which is geology, geophysics, or anomaly and geology. Yeah.
Yeah. May I add to that? Rex raised a very important concern here. We see this as a complementary tool rather than a single tool that you can use for everything. We see this to be something you can use for an area. If you're starting out, of course, you can do this and then correlate it with surface mapping, with drilling later, or other geophysical and geological means. But what we're saying is that, of course, like everything else we do in geology, this has to be a multidisciplinary work. We're not saying that this is a solve everything tool. We want to complement this with other data. There's a question there about the cost. We see this to be well, because of the short time it takes to create the map. For example, we can survey for 2 days, 3 days in, say, about 4 square kilometers area. We can finish the survey in 4 days. Okay, do data processing in 2 weeks, and the instruments involved may be around 30 instruments that are produced by us. We produce our own instruments, we bring it to the field, and then cost of installation, data processing. The software is in-house. So it's mainly the cost of taking the field survey and bring it home and data processing. That's basically what we're paying for here. Of course, we committed this to be initially as a tool to help Filipino exploration work, okay? But Rex said that, okay, why not share this to our neighbors? We don't mind doing that. And this is to lower your exploration costs. We want to lower your exploration costs. We can collaborate, work together. The cost will be low, but of course, it has to be sustainable.
Good, thank you for the details answer. Now we move to the next question, which is also about the mineral exploration. The audience asks, how accurate of this mapping in context of mineral exploration, plus can it be the main tool for the exploration study?
I think this was answered by Dr. Ramos in the previous
I
question.
think just to give an answer or an idea about that, I think this is the only thing that promises 3D high resolution geologic mapping. Okay, how it can, like any other tool, how accurate it can be depends on the user. Basically, what we're offering here is that you have a tool for creating the structural map, and we have a tool, the same tool, that you can use for mapping the anomalies. Now, how to interpret that? It still boils down to geology. A good geologist can make use of Excel and create a good science out of it. That's what we're trying to provide, a tool for you to use. Okay, accuracy depends on the user.
Thank you again. Another question from Leka about the resistivity. He asked which color show high or low, so we understand which lithology or liquid related being involved.
Yeah, I don't think it's for us to say one color represents one value. As I said, we're not trying to be quantitative there. We're trying to be more showing the contrast, showing the structures. I think you should look at this initially as like 3D seismic, that you have the structures, but you have to put in the wisdom on how to interpret it. So in that, you have the anomaly, and it's up to you to correlate it with your drilling, with your geology, with your geochemistry. And that's what we want to provide. Okay, we don't want to provide all the values because we're going to spend a lot of time analyzing, and we want more to do more examples at this time and try to find out the spectrum, as I said, of what we can explore rather than focusing on the calculations. We're not, what I'm saying is that we're not actually prepared to do the calculations. We've seen some calculations about this similar system in other parts, particularly in Europe. I'll give you a hint. It's one university in the Netherlands, and that's where we're also applying for patent.
So much, Doctor. Another question I would like to ask, how much does it typically cost to set up this 3D geological mapping using electromagnetics? For example, the cost, machine, and equipment and software involved.
I think this was answered previously. Earlier, yeah.
So next, can this be acquired using any model of the resistivity equipment out there, or do you have recommended equipment manufacturer?
Interesting question. That's a very interesting question. You know what? Some people tried doing this with cable system. You can see people saying, "Oh, we can do this with a cable system." We've found that. We've seen that. What we're offering is a nodal system. Okay. So I think you can find a system that would be cable and would promise you 3D. And we're trying to exceed that because we are providing the freedom from cables. We're providing the nodal alternative.
Okay, thank you. Other question he asked, thank you for interesting technology. May I know how much the estimated price to you to provide that that you represented from the site work to the full report?
Oh yeah, I think you would need to coordinate with Rex about costing and everything. This has to be case to case, you know. We cannot just give you a generalized form. It all depends on deployment, where you are in the world. Like right now, we're working out of the Philippines. We want to establish offices wherever we're needed, but I don't think that would be convenient for us. We're a small team and we want to work with you. Basically, we want to work with whoever's interested and let's collaborate. I think that's the main issue here. We're trying to raise. We're all from Asia. We're all from neighboring countries, and that's what Rex was trying to open up here. That look, this is not limited to the Filipinos. In fact, we're working right now with some American and Canadian people, but we don't want to limit it there. We want to share this with our colleagues in the neighboring countries.
Thank you. The last question from Ruslan also. Thank you very much for answering my first question and those about time and cost. They ask, are there any environmental concerns or limitation of us related to the using this tool? I hope see further update of this technology for geothermal application for sustainable development. Maybe this can be presented in the World Geothermal Congress 2026 call for abstract is open until 10th May 2025.
If that's addressed to me, I would say yes, sure. Let's talk about this. We're interested to find other cases. Of course, we're interested in the business, and we're interested to collaborate with you. Therefore, yeah, we'd like to present this in conferences. We'd like to work on case studies with you. Sure. Let's target to be working on cases and collaboratively work on something to present somewhere else. Yeah, very interested. Thank you.
Based on the question of Rosanel, she did mention something about environmental concerns or limitation using this tool. As what I mentioned on the presentation, this is a passive method wherein we just use ubiquitous electromagnetic waves being emitted by the structures at subsurface level. So we're not we're not doing like seismic wherein you have to have an active system going on in that area. I mean, it's in terms of environmental concerns, it's really really friendly. I mean, using this method.
Thank you, Doctor. Any other questions? Please feel free to ask.
Okay, let me thank all of you for being interactive and having interest in what Rex and I are talking about. So yeah, just give Rex and myself a message. Let us know what's going on. Thanks, Dr. Hariri and Abdul Mahid,
Majid.
all the
Yeah.
coordination. Thank you,
Yeah.